I'm going to derive the equation for osmotic pressure. And the physical situation is we have a semi-permeable membrane. What that means is that only the solvent can go through the membrane. So on the left side, the green is only solvent. On the right side, we have a solute-solvent mixture. For example, left side could be water and the right side could be water with, say, sucrose dissolved in it. And what we see is that at equilibrium, we have a difference in height. So this difference in height, call that H, that corresponds to a pressure difference. And this pressure difference is the density, the acceleration of gravity, and that height. So in this case, that's the osmotic pressure for this solution on the right side. And if we want an equation to relate that to properties of the system, then what we're going to do, and we're going to do all this for the solvent, because we have the solvent on both sides of the membrane, we can have an equilibrium relation that the chemical potential on the left side for the solvent equals the chemical potential on the right side for the solvent. Now it turns out it's easier to work with fugacity than chemical potential, and so I'm going to write this as the fugacity of the solvent on the left side is equal to the fugacity of the solvent on the right side. I'm going to put a hat over that fugacity on the right side to indicate it's a solution, whereas on the left side it's a pure material. So on the left side, the fugacity of the solvent is calculated at the pressure on the left side. So left side, right side, pressure here, pressure here. And on the right side, the fugacity of this mixture is going to be the mole fraction of the solvent, the activity coefficient of the solvent, and then the fugacity of the pure solvent, but evaluated at the pressure on the right side. Now we start simplifying this, and first we set this equal to 1. Because the mole fraction of the solvent, it's going to be 0.9697, very close to 1, which means this is almost all solvent, and so the activity coefficient, of course, as x goes to 1, has to be equal to 1. And so it's a reasonably good approximation that that's 1. Now let me write this equation again. Solvent pressure on the left side, the mole fraction of the solvent. Now the fugacity of the solvent at this pressure on the right side, we can write it in terms of the fugacity of the solvent, the pressure on the left side, and then the pointing factor corrections. And so what this is an exponential. This is the molar volume of the solvent, pressure on the right side minus pressure on the left side, a gas constant, and temperature. So this whole term is the pointing correction. So this difference in pressure, this rho GH, which corresponds to the osmotic pressure, and so we're going to use the symbol pi for the osmotic pressure, so that's that pressure difference. If we look at the equation, pure component, the solvent fugacity at pressure on the left side is equal to that. So that term cancels, and so we can simplify. So let me pause and write down the equation with these changes. Now what I'm going to do is just rearrange this equation to solve for the mole fraction of the solvent. And now that I've rearranged it, and notice the minus sign as we brought the exponential to the other side of the equation, I'm going to take the log of both sides. So we have the log of the mole fraction of the solvent, and then on the right side we have this term. Well, it turns out there's a mathematical simplification that the log of the mole fraction of the solvent, when that mole fraction is close to 1, can be approximated by just the mole fraction of the solvent minus 1. And so let's make that substitution, and then realize that the mole fraction of the solvent plus the, so let me write this down. So the mole fraction of the solvent plus the mole fraction of the solute must add to 1. So if I say mole fraction of the solvent -1, that's going to be minus the mole fraction of the solute. So this then is the mole fraction with a minus sign of the solute. Well, we can rearrange this. We have minus signs. So we're looking at this term is equal to this term, minus signs on both sides. So I can write the osmotic pressure, molar volume of liquid solvent on the left side. I'm going to have mole fraction of the solute times RT on the right side. And so this equation then is the equation for osmotic pressure. And I mentioned at the beginning that we derive this assuming a molecular solute. If we have instead something that dissociates, then we actually have more species in solution. Entropy is higher. We have to account for that, and we account for that with this term that's the Van Hoff factor. So for example, if we had sodium chloride and it completely dissociates, then this Van Hoff factor would be 2. And to give you a physical feeling for the osmotic pressure, if we look at seawater, the osmotic pressure is about 28 bar. So fairly high value, and that's 3.5% concentration of salt in seawater.